And so we bring up the slides. No questions, comments?
Professor, last time
Yes.
you have a full model, you said the name is M, and change it
Yes.
to restricted model as M1. Could you say again how you find the 1n time gamma?
Yes, I'm going to go over that. Thank you. Let me just see if I have the right slides. Something is missing. Sorry. We'll try. Okay, so just give me a second, see if I can do this. Okay, this is good. I have to share my screen. Okay, so the question, so we were doing this example, and I guess your question is, what is, so how we get, so we had this full model, right? So if you look at this, this is the model that we used. The, sorry, okay, so the response is the final cholesterol level, and then Z is the initial cholesterol level. And these X's are the indicator variables determining whether the subject has taken drug 1, 2, up to 5. So we wanted to test whether the betas are all the same. So the restricted model could put this constraint, beta 1 equal to beta 2 equal to beta 5. And then I can call that the constant number, gamma. So all of them have to be equal to the same thing. So that same thing I call gamma. And the new question is that how we get from that full model using the constraint to this restricted model. Is that the question?
Yes.
Yeah, okay, so maybe should I ask you if anyone else sort of got this one? Maybe one of you can, who understood why this is the case, can explain why, for example, we got a 1 times gamma here. Anyone remembers how we did this?
I just know when you say the all beta is equal, you make a matrix as a capital X with Z, X1, X2, X3, X4, and X5. But I don't understand why you say when we say X1 plus X2 plus X3, X4, and X5 is 1n. Why? Yeah, exactly.
Yeah, so this is the model, right? So you can write it in matrix form or just in this expanded vector form. So what I'm going to do is I'm going to go and set all of them equal to gamma, right? And if I do that, if I set all of them equal to gamma, then what I would get is, so let me try to do it here.
Possible.
So y x1 plus x2 plus dot 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 x5 is equal to 1n. So the reason is, so this is 1, let's say n1, 0, dot 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 0, let's say n2 up to n5. This is x1, and then I have 0 here, and 1, and then 1 and 2, dot, 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 0 here, right? And the last one is going to be 0 here, and 1, 0 and 2, dot, dot, dot. The last one will be 1 and 5. So nk is the number of subjects who took drug K. Okay, so and I can see if I add this up in the first block, I have 1 here and then zeros here. I would get 1 and 1. In the second block, I have 0 here, 0 elsewhere, and then 1 here. So if I do it, I get again 1 and 2. And the last one has zeros everywhere except the last one, which is 1 and 5. So I get 1 and 5. And this is just the vector of all ones. Right? Does that make sense?
That one, yes. Could you back in the top? You have a matrix A in the top.
This one?
And A matrix.
A? Oh, A?
Yeah.
Yeah, you mean this one?
Yeah. Here you say, for example, x 2 is negative 1, 0, 0.
No, X is not beta 1.
Oh.
So this matrix is talking about the betas. This
Okay.
has nothing to do with X.
Okay. Thank you.
Right, usually, no problem. Usually we don't use this A, at least in this course, because you can enforce these constraints directly. So enforce them by setting them all equal to gamma, and then you go in this regression, you just plug this gamma for beta. So you go and then set gammas here, so you get y is equal to alpha z plus gamma times x1 up to x5, and then this one you can see that it's 1n. Okay, so you directly enforce your constraints. You don't need to use the A matrix. This is A matrix is good if you want to solve this constraint optimization problem. If you can't directly, so if this A is complicated, you might not be able to basically solve for beta. Here, effectively, we solve for beta. So beta is not unique, but you can just write beta explicitly as beta 1 equal gamma, beta 2 equal gamma, to beta 5 equal gamma. If A is complicated, you can't get a nice, let's say, closed form solution. And then you have to solve this optimization problem using numerical methods. And then that's going to be useful. So the general form is useful. But usually in this course, we don't worry too much about A. It's good, for example, if you want to check whether the equations are linearly independent. So if you have the matrix, you can perform the linear algebra techniques to see if the rank is full or not, and whether you need to drop some of the equations. But beyond that, we don't usually worry about that. Okay, good question. Other questions? Did that resolve the question?
Thank you.
Yeah, okay, no problem. Okay, so other questions, comments?
Professor?
Yeah.
So for the full model linear regression, we basically we put alpha, beta 1, beta all the way to beta 5 as the traditional beta matrix. And for the design matrix, we just make the first column to be Z, the second column to be X1, and
yes.
then, okay.
Yes, exactly. So that would be, you would do Z here, and then X1. These are the columns up to X5. That would be your design matrix. And then your beta would be alpha, beta 1, beta 5. And then you would have epsilon. This would be your beta vector. Right? So you should just understand what the linear regression is. You don't necessarily have to have a design that has an intercept as the first column. So here, for example, the first column is just going to be this Z. And then the names of the parameters need not be beta 0, beta 1 up to beta 5. We could have called alpha beta 0, but to avoid confusion, we've called it alpha. It doesn't matter what you call them. You just have this general form, x beta plus epsilon, whatever x is, whatever beta is. Okay. Good question. So other questions? Okay, so now what I would like to do is, so we did this once for this hypothesis. The last time I also talked about, so when you do this, you get a new model, which is, you enforce the constraint, you get this M1 model, which has two parameters. You fit the model, and then you compute the residual sum of squares for that model, which turns out to be this, 2930. And then you find the residual sum of squares, or the SSE, sum of squares of errors. This is called sum of squares of error, or error sum of squares, or residual sum of squares, whatever you want to call it. This SSE is for the full model, and the difference, using that Pythagorean theorem, the difference is going to be the extra sum of squares. So this guy is equal to the difference. And you have 4 constraints in this case, so you divide this by 4. And then the denominator is just the residual sum of squares divided by n minus p minus 1. This is basically like s squared in this case. And so then you get a statistic, and you know that the distribution has to be f with 4 and 44 degrees of freedom, and so you can compute the p-value. And in this case, the p-value turns out to be bigger than the threshold that we want, so we don't reject the null. So we don't reject the null, which means that we're going to keep this M1 model, which is restricted or simplified version of M. So we favor this simpler model to the full or more complex model. Favor M1 over M. And this is a simple example of doing model selection. Between these two models, you selected M1 using this f-test. Okay. Then we can move on and ask whether these drugs have any effect. So we've determined that given the sample size that we have, the data we have, that these drugs don't have any difference. That's the null hypothesis that we just tested and we kept. Now we're going to test whether they have any effect at all. They might have equal effect, but if they equal, that effect would be 0. So now we want to test, for example, whether all of them are equal to 0. And if you expand this, you just can argue that you have 5 independent constraints: beta 1 equal to 0, beta 2 equal to 0, up to beta 5 equal to 0. So that Q is going to be 5. The degrees of freedom, the sum of squares is going to be 5. And what we need to do is now we need to fit this restricted model. So when I enforce the restriction, basically it adds another restriction on top of this restricted model. So I set gamma equal to 0 here. Or you could have just set all the betas equal to 0 in this model. Give you the same thing. So set all the betas equal to 0, you get the restricted model, which is y equal alpha z plus epsilon. Okay, so we get this this null model. So the null model is this M2. I'm calling it M2, which is a further restriction of M1. And then I fit this. So I fit this, you get, for example, fit this alpha hat. Anyone knows the formula for alpha hat if I fit this model? Off the top of your head, how do you get the alpha hat? Using the least squares estimate.
Is it like ZTZ, the whole thing inverse, ZTY?
Yes, so that would be the least squares estimate. And in this case, it's just going to be Z transpose Y divided by Z transpose Z. Why?
Because of the dimension. So ZT is like 1 times some 1 times n, I guess.
Yeah, ZT is 1 times n, Z is n times 1. So this is basically the square norm. So another way of writing is Z transpose divided by Z squared, norm squared. So Z transpose Z is just scalar. So in this case, you just compute this. And then from this, you get that E m2 squared would be, for example, y minus alpha hat times Z. So you know y, you know alpha hat, you know Z, you can compute this. So that's how you do this. And it turns out to be this number. Okay. So let me ask you the question. So compared to, so we had the residual sum of squares for the full model, which I usually don't write m here. So this is the full for the full model, basically this. And I have the residual sum of squares for the restricted model, the first restricted model, and now I have the residual sum of squares for this guy. So we saw that this is bigger than or equal to this. So how about the relation between these two guys? Which one is bigger? Should be bigger.
M2 should be bigger.
Yeah, why?
Because so in addition to a restriction on M1, there's one more restriction. So it is supposed to be bigger or equal to the residual of M1.
Yes. So this model is a further restriction of M1. Okay, whenever you restrict a model further, the whatever is down the line is going to have less explaining power, is going to have higher SSE. So M1 is nested. So you can say M contains M1 and M1 contains M2, or M2 is inside M1, M1 is inside M. And so you have this nested relation. And so the SSEs go the other direction. So the bigger model has a smaller SSE. The bigger the model, the smaller. But they have to be nested. One has to be a restriction of the other one. Okay, so this turns out to be this, and you can compare it with the values that we have here. You can see it's bigger than both of them, which is good, which is what you expect. So now I had the previously computed the SSE for the full model. I had the SSE for this model, and then I subtract, I get the extra sum of squares. Okay. So then you can compute the FS statistic, which is the extra sum of squares divided by the degrees of freedom. Its degrees of freedom, which is 5, and then the denominator is the same. So same as before. Same as this extra the SSE of the full model divided by the degrees of freedom of that SSE, which is 44. And so you get 3.18, and this thing is going to be an F distribution, or has an F distribution with 5 and 45 degrees of freedom, and then you can compute the p-value, which is turns out to be 0.02, and so you reject this null. So there is some evidence of the Krug effect. So we favor M over M2. So if you do this test, you favor M over M2. And that's it. So between M and M2, we pick M2. Sorry, M. So if you compare M and M2, you pick M. If you compare M and M1, you pick M1. Okay. So do we go with M or do we go with M1? Generally, you go with the simpler model. So you're going to go with M1. Between M and M1, when you pick M1, you're going to keep M1. So M1 is going to be good. So in this case, we have that the drugs have some effect, but their effect, there is no difference in their effects. So that's the conclusion that we got here. Okay, questions? So it's a good time to ask you a question, which is going to be interesting. So let me add this here, add a page. This is really messed up. Okay. This is bad. Sorry, let me try to see if undo. Why did I get this here? Sorry. Let's see if I have. Okay. How can I get the? Oh, bad. Sorry. Add one page here. Maybe that's it. Okay, so that's what I want. So now let's say I have e squared, which is equal to so this is, let's say, e squared of m, I would say 2, 9, 30. Sorry, this is 2505. And then I have e of m1, which is 2, 9, 30. And then I have e of m2, which is equal to 3, 4, 1, 0, 68. Okay, now, so m is y equal alpha z plus beta 1 x1 dot 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 beta 5 x5 plus epsilon. M1 is y equal alpha z plus gamma times 1n plus epsilon, and then M2 is y equals alpha z plus epsilon. Okay, so I've compared these two guys, and I also have compared these two guys using the t-test. Now we can also compare these two, M1 and M2 direct. So can I compare them using an f-test? Is it possible to do it? And if so, how should we do that? Can I write a hypothesis test that compares these two? Do an f-test of this. Maybe think a little bit about this, just 1 minute, and then we'll come back. So how to perform a test between M1 and M2 using the a hypothesis testing and an f-test.
Also, we can use the image of, for example, M and M1 for statistic for null test. For example, the mu hat minus mu hat M is 0.
Sorry, can you say that again?
If we want to compare M and M1, I use mu hat M minus mu hat M1 is 0.
Right, okay, so, sorry. Mu hat, sorry, mu hat M1 minus mu hat M2 is 0. Is that what you?
Yeah.
Why is that?
If we look at these three models, just the difference is to image of X, or I think.
Right, so you're looking at these two models. So you're looking at this one and this one. When you fit the first one, M1, so you have, let's say, Z, and then you have, for example, 1N. So what you end up doing is that you project onto the span of these two vectors. So that would be the, let's say, L of X of M1. That's if you think of the design matrix. So X of M1, let's say, it would be just Z, for example, and 1N. And L of sorry. X of M2, which is Z and just itself. That's the, right? So in this picture, what would be the image of X? So let's say L of X M2 would be just the image of X of M2. What is the image of X of M2? Anyone knows?
Is it like the case when we try to test whether like a certain entry in the parameter vector is 0? So like when we used to have a beta and we want to test that beta I equals to 0.
Right, that's correct. So you could also do that. So that's a very good point. You can do this test using a t-test as well. I'm going to come back to that. That's a very good point. But let's for now just figure out the f-test, and then I'm going to talk about that as well. So what is the span of the column space of this? This is a linear combination of the columns. Anyone? This is a vector.
It's Z.
Yeah, go ahead.
It's Z.
The span is Z.
Yes.
It's a single vector.
It's the span of Z.
So what is the span of Z in this picture?
It's a line.
Which line?
The line along Z.
Yes, okay, so that would be L of X M2. Okay, and then when I have Y generally does not lie in either one of them. So when I'm going to project Y onto this guy, I get this would be mu hat. So when I project it here, that would be mu hat M1. And when I project it onto the other guy, I get mu hat M2. So in general, they're going to be different because these are different potentially subspaces. So one is nested within the other, as you can see. So this subspace L of M X M2 is inside L of X M1, which is what we sort of observe. M1 is nested within M2. So that's this relation. Okay. So M2 is a submodel of M1, which you can think of it as the image of the design matrix for M2 is inside the image of the design matrix for M1. And so this is not going to be in general 0. So in general, it's going to be non-zero. Okay. So now, what can we do if you want to do an F-test? So when you want to perform an F-test, you have to pick one model as your general full model and the other one as the null or restricted model. Which one should we pick as the full model? Which one as the restricted model? Anyone?
Maybe M for the full model and M2 for the restricted.
So if I do that, I take M as the full model and M2 as the restricted model, then I'm going to perform this test. I'm going to compare M and M2. I'm going to perform this test, right? So already done that. I want to perform directly M1 and M2.
Okay, so M1 for the full and then M2 for restricted.
Yes. Right, so M1, take M1 as the full model. And M2 as the null, aka also known as restricted model. Okay, so so when we want to do the F statistic, what will be the denominator? Anyone?
It should be EM2 squared divided by 5.
So yeah, so that would be the SSE of the full model, which is in this case this guy. So SSE of the full model. And the degrees of freedom, generally, if you want to remember, it's just going to be n minus the number of parameters in the model. How many parameters do we have in the model?
1.
Right. So it's not going to be, it's not going to be 5. It's going to be, how many we have here? It's going to be, n is 50. Right. So you get, sorry, this is, you said this should be the full model, not the restricted model. So this would be M1. So that wasn't correct.
All right.
Right. So this should be this, and then we have 2 parameters. So number of parameters. In M2. This is like P plus 1. Okay. So how about the numerator? So the numerator we can write as this additional sum of squares. M1 minus mu hat M2 squared divided by what will be the degrees of freedom. So the degrees of freedom will be the number of restrictions that you impose from going from the full model to the restricted model. So how many restrictions to go from M1 to M2?
1.
1, yes. So that would be the F statistic. But so at this point, you can compute all of these. You fit the 2 models, you can compute all of these quantities. However, I have given you this information, okay? Just given this information, can you compute this? Remember the approach that you did here. So extra sum of squares can be written as a difference of 2 SSEs. So what would be the SSEs here?
Is it like EM2 squared minus EM1 squared?
EM2 squared, yes. So the smaller model has bigger SSE minus this divided by 1. And then I have EM1 divided by n minus 2. So this would be what? 341,068 minus 2505, right? And then divided by 1. No, sorry, this is 2930 divided by 1, and then 2930 divided by 50 minus 2. Okay, and so what is the distribution of this under the null? I'm going to write it under M1. So the null would be under M1. Under M1. What is the distribution? It will be F with how many degrees of freedom? You want?
1 and 48.
Yes, 1 and 48. Okay, so let's see if we did this right. Okay, we did it incorrectly, but I guess that's the incorrect one. So yeah, so this should be correct. This should be incorrect. So this part is correct. This should be 2, right? And what we need here is 48. Should be 40. So I have to fix this. So that was the problem there, but otherwise, so this is correct. Okay, so when you compare these two models, there is no m in the picture. So you just throw m out. So now you just treat this as your full model and treat the other one as the restriction. And this guy has 2 parameters. So the SSE would be divided, this is the degrees of freedom, the SSE n minus the number of parameters, and the difference of the number of parameters would be 1. Okay. Yeah, although this degrees of freedom is not correct, but in this case, this has to be corrected. So this is not correct, this is not correct, but you end up favoring, this is the conclusion is correct, you end up favoring M1 over M2. Okay. So if you compare them, if you compare M against M2, you go for M. If you compare M against M1, you go for M1. And if you compare M1 against M2, you go for M1. So M1 seems like the right model here. Right. Okay. Does that make sense? Questions? So if you understand this example, you at least understand how to apply the F-test. And then you can use it to compare different models as long as they're nested. Questions? Okay, seems like people are okay. So that's just the same thing. Right, I'm gonna skip this. Yeah, so a summary of this, these ideas is that there is duality between statistics and linear algebra. So you can translate things from linear algebra to statistics. So for example, subspaces are like models. So this was the full model, for example. This is the image of the design of the full model. So you can think of L of X as modeling your mean vector in the full model. And this guy, alternatively, I've written this as like L of XM, for example, and L of XM1, for example. You can think of it this way. It's a little bit slightly better notation, I would say. And So these represent, the subspaces represent models for your mean, the mean vector, mu. And the subspace relation, one inside the other, represents the nestedness of models. So submodel relation. So L of X, La of X is inside L of X. Then the model associated with A is inside the other model. And projection in linear algebra, projection into L of X is equivalent to fitting the model. When I project, I get the fitted values, and from that you can just get the parameters. And the residual sum of squares is, this is, in this case, it's just the norm of the error of projection. Norm squared of the error of the projection. And in the context of statistics, this is just the unexplained variation by the model. So you pose a model for the mean of Y. You can have other nested submodels of it. You fit these models, and then there is some unexplained variation. So in the linear algebra framework, you have subspaces. These subspaces can be subsets of each other. You project onto these subspaces, and you have an error, and then you can look at the sum of squares of the error. So these basically are the same. At least in linear models, there is this close connection with linear algebra. Okay, I'm going to skip this. So that's the this set of slides. Any questions? Okay. Don't worry, you can still ask questions. We're not going to leave this topic, but this this part is going to go over some more special cases of the f-test. So the f-test that we just did, so you have a linear model. Let's say this is general linear model. Beta, so you have some intercept, for example, here, and some covariates here, and the noise. And we did the test that these coefficients. So when you test the coefficients that are, let's say I test the coefficients other than t-intercept beta 0. So if I test whether all the coefficients except beta 0 is equal to 0, that would be this null hypothesis. And this is generally called an Anova, analysis of the variance. The f-test in general can be called an analysis of variance, but sometimes this special case is called Anova. And the name doesn't matter. It's just that oftentimes, for example, people perform this test to see if there's any linear relation, if the model is good or not. So you can just test. So the restricted model in this case is going to be just the model that has a single intercept. Okay, this is a very basic model. You can think of it as the baseline. And you're testing whether your linear model can compete against this baseline. So if I take this simple model as the null, and if I cannot reject this null, then it means that probably there's this term is not necessary. So probably Y is not related to Xj's at all, at least not linearly. Okay, and so sometimes this is called sometimes called a test of significance of the linear relation or linear model. So if, for example, someone asks you to do a test of significance for this model, or whether this model is significant as a whole, then this is a good test to perform. Okay, and there's nothing new here. It's just a special case that's good to remember. There are some things that you can do, for example, because the restricted model in this case is very simple. So we can compute, for example, so what is the estimate of beta 0 in the restricted model. So if I fit this model, what would be the estimate of beta 0? Anyone?
I'm not sure, but I guess it's close to y. Close to.
So can you give me a formula for it? I'm going to write this beta hat A0. Or
Right.
I'm going to call it beta 0A to not to be confused with beta hat 0 in the full model. So what is this?
Equals to 1 transpose times 1, which should be n.
Right, inverse, let's write it full, right? 1 transpose y, and then this is n. So you get 1 over n, 1 transpose y. So what is 1 transpose y?
1 transpose y is ny.
No, y is a vector.
Yes. N
right?
times y, I mean.
This would be 1, 1, 1, 1, 1. And then y1, y2.
Oh, sum of y, sorry.
Right. So this would be 1 over n sum yi, sometimes written as y bar. Okay, so this is just a sample average of the y. So if I fit this model, the restricted model, this is my estimate. My estimate of beta 0 is just the sample average. Okay, and so when you compute the SSE for the restricted model, you just plug in this, I'm going to call this beta hat 0a here. And so I would have this guy would be y minus beta hat 0a1 squared. And so this is just basically y. So if you expand, it's just going to be summation I from 1 to n, right? yi minus beta hat a0 times 1, because the coordinates of the second vector just are all 1, this one are all 1. So that's the definition of the norm. And this is just summation I from 1 to n, yi minus y bar squared, because that's what we did here. So, right. So what you get is that the SSE for the restricted model in this case is just the sum of squares of the deviations of y from this mean, and this is sometimes called the SST. Okay, this has a name, total sum of squares, or sum of squares total. Right. So the SSE, if I call this M0, for example, model M0, the SSE for the restricted model M0 is called the SST for this. And you can see the SST is just depends on the response vector. So you can think of this basically some of the deviations of y from its sample mean as the SSE of a baseline model. And so the difference, so this extra sum of squares would be this guy, which is the SST, minus this is going to be the SSE of the full model. Okay, so the F test would be SST. So F a statistic would be the SST minus the SSE divided by something, and then SSE divided by something else. So now you tell me what the degrees of freedom would be. What is the degrees of freedom for the numerator and the denominator? So think of this. So what is the degrees of freedom of the SSE for the full model? Anyone? So the degree,
For full model is n minus p plus 1.
right, so it's always n minus the number of parameters. The degrees of freedom of the SSE for the linear model is n minus the number of parameters, which is p plus 1. So what is the degrees of freedom of the extra sum of squares? SSD minus SSE. That would be the difference between the number of parameters of the two models, or the number of restrictions. How many restrictions did we put to get the normal?
2 minus 1 is just 1. Or is p minus 1.
Yes, so it's p plus 1.
Yeah.
Sorry, not p plus 1, p, because you have p constraints.
Yeah.
So this is going to be p. We have p constraints in going from the full model M to the restricted model M0. So if I call this M, and if I call this M0, then the difference between the number of parameters is basically in this case, more or less, always the difference between the number of free parameters. So you have one parameter in M0, p plus 1 parameters in M, and so the difference is p, or you can see you have p constraints here. Beta 1 is equal to 0. Beta 2 is equal to 0, Beta p equal to 0, p constraints. Okay, so that's it. So you can compute this. So you fit the full model, you get an SSE, and the SST is just easy to compute. So fitting the normal model in this case is trivial, basically. And then compute this, and this has to have how many degrees of freedom? This is going to have like an F distribution with p and n minus p plus 1 degrees of freedom. Okay, and then you can also do a little bit more. So I can, for example, there is, with every sum of squares of error, there is a degree of freedom associated with that. So what is the degrees of freedom associated with the SST? So the SST is the SSE of this model. So what is the degrees of freedom of the SSE of this model? It's always n minus the number of parameters. How many parameters do we have?
I have just plus 0, it's just one parameter.
Is one parameter. So what is the degrees of freedom of the SSE of it?
N minus 1.
Yeah, so that would be n minus 1, which is going to be just the degrees of freedom of SST, because SST is the SSE of that model. And then you can see that these numbers add up. So so you see here, the this is the SST. This is the SSE of the full model. Usually you just call it as SSE. And this is like the extra sum of squares. And you can see the degrees of freedom also match the degrees of freedom of SST plus the degrees of freedom of the SSE gives you, So in terms of degrees of freedom, this is n minus 1, this is n minus p plus 1, and this is p. Okay, so if you add these two pieces, you get this. Okay, so the degrees of freedom add up. Okay. So this turns out to be a very messy slide, but hopefully you get the idea. Okay. The only thing that's different here is just a bunch of names that we have given to these quantities, and the fact that fitting the normal in this case is trivial. You just can do it once, and that will be the SSE of the normal, which is called the SSE. It's just nothing new here. And this is usually summarized in an Anova table. So you have the SST here with its degrees of freedom, SSE with its degrees of freedom, SSR. So this thing here is going to be called SSR. So this is called SSR, or sum of squares of regression. Okay, that's the other name for this. Regression sum of squares, or sum of squares of regression. Okay, so these have some names. So this would be, the F statistic would be SSR divided by P divided by SSE divided by N minus P plus 1. Distribute like FP and N minus P plus 1. You don't need to memorize this as long as you understand the F test. You should be able to get this every time. Just remember the names here. So SSR, SST, SSE, SST. So SSE is just the SSE of the full model. So you summarize this in this table, and then SSR divided by P, this is called the MSR, mean squared. Mean squared is mean squared of regression, or regression mean squared, something like that. This is the MSR. And this other guy here, or maybe different one. This is just called the MSE. Okay, SSE divided by, so mean square of error. Mean square of regression and mean square of error. Okay. And then the F statistic is just the ratio of these two mean squares. Okay. Does that make sense? It's just a way of summarizing, and you can see, for example, if you do it in R, it produces this table. If you do Anova, this is one version of Anova, which is. But you can also construct this table for comparing any two models. So all the three tests that we did for the OC example, you can write it in this format. Okay, so there are some other formulas which in homework problems or as an exercise, maybe I've assigned it, maybe not, but there are different ways that you can write the SSR, and you just have to use the properties. For example, some of the properties is that E is orthogonal to X beta hat, or mu, right? This is from the linear projection idea. So for example, if I write y minus E squared, that's the, sorry, I want to compute, for example, yeah, I'm not gonna do this. So as an exercise, do this, and you can use these geometric ideas to simplify. So E, for example, should be orthogonal to X beta hat, and so on. Okay. Okay. Questions? All good here? So let me, well, we're going to give an example here. So before doing that, so there is also this concept of coefficient of determination, or R squared. Have people seen R squared before? How many people have seen R squared? Maybe you can say yes, no in the participant window. R squared. You should have seen it before. No? Yes. A very quick yes. Other? Okay, so people have seen it, I would say. It's just SSR divided by the SSD is called R squared. And we know from this relation that we had here, so because remember, SST is equal to SSR plus SSE, and all these terms are non-negative. So SSR is going to be bigger than 0, less than SST. So SSR divided by SST would be between 1 and 0. So it's a number between 0 and 1. Or you can use this relation to write it as 1 minus SSE divided by SST. Okay, it's just going to be generally a number in 0 to 1. And 1 is better. So if it's 1, SSE is 0, and you have a perfect fit. So regression sum of squares is the same as the SST. You have explained all the variation. So this is sometimes, so let's say, you can think of this as unexplained variation, and as this one as the explained variation by the model, unexplained by the model. And so if SSE is 0, all the variation in Y is explained by the regression model, and you have a perfect fit. And in general, it measures the strength of the linear relation between Y and X. Okay, it's good to remember that it does not measure the effect size. So it's not saying that whether, so for example, Y is like, it doesn't say anything about the size of the betas here in this model. It just says that this model is a good fit. Betas might be small relatively, but noise might be smaller. Okay, so relative to the noise, however you're doing. So betas could be really small, but the noise could also be small, or we could perfectly fit the model, and so it's a measure of strength of the linear relation. So there's a subtlety. So it's how well the model fits. And if you change the model, if you add or remove some of the variables, the R squared changes. By looking at the R squared, you can do some sort of a model selection. Although R squared itself is not a good way of doing model selection. So if I drop variables from the model, generally R squared increases because you have less parameters in the model. You can see, for example, if I drop all of these, I get that. And so the SSE goes up, we have seen. When SSE goes up, SST is the same because Y hasn't changed, then R squared goes down. So the more variables you drop from the model, the larger the R squared gets. So, sorry, the smaller it gets. So if I drop the variables from the model, SSE goes up, R squared goes down. If I add variables to the model, SSE goes down, R squared goes up. So in general, you can keep adding variables to the model until R squared is equal to 1. And this happens in general if you have n-1 variables, because then you also have an intercept. So you get exactly n parameters. So you get n-1 parameters, n-1 parameters plus 1 intercept. You get n total number of parameters. So you have n parameters and a sample size n, so you get an n by n linear model, and in that case, you can perfectly fit. So you can make the residual be 0, because generally the image of x would be the entire Rn, and Yn is in the Rn. So when you project it onto Rn, you get Y back itself. So mu hat would be Y, and the residual sum of squares would be 0. If x in Rn is full rank, then the image of x would be just Rn. So from this, again, mu hat would be 0. Sorry, mu hat would be the same as Y, and the E would be 0. And so R squared would be 1. But this is not necessarily good. So this is an example of an overfitting. So when you have too many parameters relative to the sample size, generally you also fit the noise, because you'd expect that Y's contain noise. You don't want to perfectly fit to the Y. And this is an example of the overfitting, which you have to worry about. So there are better ways to do model selection. Generally, you want to add variables until the R squared sort of does not change much. So it's going to always go up, but at some point, the change is not that much. So then you try to stop. We can formalize this more when we talk about model selection. But just remember these things about R squared. So it's a good measure of how well your model fits. And by changing, like adding and dropping the variables, you can see the effects on R squared and can do some sort of model selection. But you have to worry about overfitting. And R squared also summarizes this test. So you can write the F test in terms of the R squared. So you can see this is more or less, this is the related to the R squared. So if you do some algebra, you can write this as a function of R squared. Then if I give you the R squared, for example, if you know the degrees of freedom, you can compute this F statistic. So that's all you need to compute the F statistic. Okay, questions? So let's see an example. And also, I have to go back. I think either Shushen or Chen, one of you mentioned that something in the previous example, which I forgot to get back. So I'm going to get back to that. If I forget, just remind me about the last test that we did. There was an interesting comment pointed out. I'm going to go back to this. So let's do this example quickly. So we have the gas consumption example. And here we have a linear regression model. P is equal to 6. So you have 6 variables and an intercept. So Y here is, so this is a car's data, which is also in R and in your board. So it's one of the default data sets in R, which so collects the data on gas consumptions of various models of cars or engine types. And Y here is going to be 100 divided by mile per gallon. So that's a good sort of transformation of the data that your book does. And so that's what it is. So, and then N is 38. And the 6 is just the number of variables in them, all different kind of weights and so other characteristics of them. So these covariates are various characteristics of the engine, I believe. And so you want to test the Anova, sorry, you want to do Anova to test whether the model is significant. So you want to test whether these coefficients are 0. So you fit the model, and it turns out that the SSE of the full model is this. Okay, and then you compute the SST by just computing this, which also can be written this way. Just do it as an exercise. This turns out to be this number. Okay, and you expect the SST to be bigger than the SSE, and you can see there is a significant difference between the two. But we can formalize this fact, whether this change is big or not. So you compute the SSR, which is the difference between these two, and it turns out to be 46.4. And you can summarize this in a table. So 46 is the SSR, this is the SSE, this is the SST. degrees of freedom. So what is the degrees of freedom of the SSE here? So what is the degrees of freedom for this guy? N is 38.
Yeah, 38 minus 6 minus 1.
Yes, minus 6 plus 1, the total number of parameters in that model, which turns out to be what? 31. Yeah, so how about the degrees of freedom of this guy?
There are 6 restrictions, so it should be 6.
Yes, 6 restrictions. And how about the degrees of freedom of this one?
So it's 31 minus 6.
31 plus 6, or 31 plus 6, or it would be n minus 1, which is 38 minus 1. Okay, so it would be 37. So 6, 31, and then the SSD is the sum of the two. And then you can compute the MSR. So this divided by 6 gives you that. And this other guy divided by 31 gives you this. So that's the mean squared. So divide these sum of squares by their respective means, right? So that's what I get. And then divide these two guys by each other, you get 79. And 79 is pretty big, and the p-value is going to be very small. So in order to have a rough idea, so you can go to the table, and so this has to be, so compare with quantiles of an F distribution with 6 and 31 degrees of freedom. If you don't have a table, it's generally good to remember that an F distribution, for an F distribution with D1 and D degrees of freedom, the mean is D2 divided by D2 minus 2. And this is the variance, so you can look it up in Wikipedia. So this has to be D2 has to be bigger than 1. Otherwise, the mean is infinite, undefined. And if D2 is bigger than 4, then the variance is well-defined, otherwise infinite. So, and this formula, you can see if I let D2 go to infinity, this behaves like 2 over D1, okay? And this, as D2 goes to infinity, approaches 1, okay? So generally, for large D2, the mean of an F distribution is close to, so let's say D2 much bigger than D1, and much bigger, or D2 much bigger than 1, then the mean is approaching 1, and the variance is 2 over D1. So you would expect that F hat is roughly like 1 plus minus, I write it as O of root 2 over D1. So it could be like, for example, plus minus 2 times root 2 over D1 or something like that. I'm going to write it as a constant. Constant could be here, C. You can take C, for example, to be 2. So this is the standard deviation. Approximately 1 plus minus something like that. Again, when D1 is large, this is going to be very small. So F hat would hover around 1. Okay, and so 79 is very big because 31 is quite large. So you'd expect this to be approximately 1 plus minus, let's say 2 root 2 over 31 if you go to a standard deviations. Still much smaller than 79. So you can quickly determine whether you have to reject or not. This is like a back of the envelope calculation. Okay, back of the envelope calculate. Otherwise, you can look at the this table. Okay, any questions? Questions, comments?
So what I understand is SSR is an error of restricting the model, and SSE is the residual of the full model. So what SST stand for?
Can you say, so SSE is the
A residual of restricted model.
residual sum of squares for the restricted model. Yes. So what is SSR, you said?
What SST stand for?
No, okay, but you said something about the SSR. So what was your interpretation of the SSR?
SSR is the sum residual of the restricted model.
No, that's the SST. So SST is the sum of residuals of the restricted model. Remember? So the restricted model is this guy. And when I fit it and compute the SSE of that model, it gives me the SST. Okay, SSR is just the difference of these two SSEs.
Right.
Okay. So SST is the residual sum of squares for the restricted, for this baseline model. Okay.
Okay.
Yeah, where should I write it? Yeah, it's going to be too confusing, but just remember this equation. This is equal to SST.
Oh,
Okay,
so
this is the,
SST.
right? Yeah, SST is, so the confusing thing is that usually in this context, there is one thing that they call SSE, and that's for the full model. But if you assign an SSE for every model, or if you call, let's call it residual sum of squares to avoid confusion, residual sum of squares for this model makes sense, and if you compute it, it's just the SST. That's how we did it.
Right. Yeah, I see. Thank you.
The difference, this difference is just the SSR, which is the extra sum of squares. So if you want, this SSR is the extra sum of squares in this test, in testing these two models. Okay, no problem. Yeah, we're out of time. You can ask questions next time. Just remind me next time. I forgot who asked this question, but when we do this test, we could test instead of doing the F test, we could test. We could test this by just testing whether in this model gamma is 0 or not. So you fit this model and test whether gamma is equal to 0, and you can do it by a t-test. And that would be equivalent to an f-test. Remind me next time to maybe say a few more words about this. But that was a great question. I forgot to get back to. Okay. If there's no comments.
I have another question. So for the special property of the F-test, you just said like the F like D1, D2, and expectation of F, the F will be like D2 over D2 minus 2. Is there any practical use for this property and also the variance?
Right, that's what I mentioned. So the practical use is that gives you, so this back of envelope calculation that I did, so if you have an F distribution like this, the expectation is like that, okay? As D2 goes to infinity, you can see this approaches 1. So if you remember your calculus, take the limit. So limit of this as D2 goes to infinity. This is just going to be limit of D2 over D2 minus 2. This is going to be 1, okay? So this is saying that if you look at an F distribution is positive, but as D2 goes to infinity, this is going to be concentrated around 1, and the variance sort of approaches this, and this is also the limit of expectation of, limit of the variance of F hat is 2 over D1. If you take the limit of this, just do it as an exercise. Just look, this is from Wikipedia, let's say. Do Wikipedia, and then you see this, and take the limit, this would be 2 over D1. So this is saying that, let's say if I go, usually if you go 2 standard, 3 standard deviations away, then it contains bulk of the mass. Okay, so for example, if I do 1 plus minus 2 standard deviations of f hat, then this is gonna contain more of the mass. Or so you could do 1 plus minus 3 times the standard deviation. Or if you want like 5 standard deviation, that would be a very good chunk of the mass. So this would be, for example, approximately 1 plus minus 3 times root 2 over d1 when d2 is large. Okay, so this gives you an interval in which your f needs to lie for you to have a high, with high probability. So the probability that an f distribution lies in this interval is high. So you can compute it. For example, what is the probability that f hat minus the expectation is between 2 standard deviation or 3 standard deviation. So let's do this. This is less than or equal to 3 standard deviation of f hat. This is going to be large, like close to 1. Okay, so in this case, for example, you get 1 plus minus 3 root 2. D1 is what? D1 is 6, right? So you can do it with 2 here or 5, let's say, to be sure. That would be a very high probability. So this would be like roughly approximately 1 plus minus 3 times divided by, let's say, root 3. Okay, and this is like 1 plus minus root 3. And what is that? This is like, anyone knows what root 3 is? 1 minus square root 3. That would be like negative. So this is saying that f hat belongs to negative 0.7 and what? And 2.7 with high probability. The probability can also compute. Okay, and because f can't be negative, they're just saying that f hat is less than or equal to 0.0 with high probability. Okay, we did this little calculation here, and in this example, you have f which is 79, which is very unlikely. I mean, it's far from this high probability interval. So in this case, you can easily reject. Okay, without having a table. So instead of looking at the table or computing it in R, you can do a rough calculation to see whether this f value is large or not. Okay. Generally, when D2 is large, f would be close to 1, especially if D1 is also large. So you can see if D1 is very large, this is going to be very close to 0. So f would be very close to 1 with high probability. And so if you observe an f value which is 79, it's very off. So did that answer your question?
Yes, thank you so much.
Okay, no problem. Okay. Any other questions now that we're at it? No? Okay, so let's finish, and thank you. We'll see you next time, hopefully.